We talked last time about oxy-fuel cutting, and we mentioned that basically you get very high heat transfer rates in oxy-fuel cutting. You're essentially eliminating the boundary layer by condensing it to form a liquid oxide. Iron oxide forms, and so the gas that's coming in this flame turns to a condensed phase, and so there is no boundary layer. And so you don't limit the heat transfer to the surface because of the boundary layer. And if you go through all that, you find that you get about a 50-fold increase in heat intensity because there is no boundary layer. Iron is the fuel in oxy-fuel cutting. It turns out it really doesn't matter whether you use MAP gas or propane, because those just allow you to start the process. Once the process is started, you can actually turn off those pilot flames because it's the oxygen that's burning the iron. And we also said that if you have impurities such as carbon in the steel, which forms carbon monoxide during the burning process, or nitrogen in the oxygen, you can lose up to 50% of your cutting speed because you will form a boundary layer, and that essentially limits the rate at which oxygen can get to the fresh iron surface. We mentioned that certain materials can be flame cut. Basically, carbon steels and titanium can be flame cut. Stainless steels are difficult to flame, or stainless steels by themselves are impossible to flame cut because the chromium oxide layer is stable. What people sometimes do is add iron powder to the oxygen jet, and now you're getting fuel. You're basically making a fuel of an iron powder oxygen flame, and when that molten iron oxide hits the chromium oxide, it alloys with it, and you can make a very ragged cut in stainless steel by adding iron powder to the system. Sometimes people do it, but not usually. And I guess the last thing I said at the end of the day last time was I was going to tell you how you cut thick aluminum. And this is a story of when I was first year. I was a young assistant professor. Industry sometimes calls up MIT, and they have some problem, and they figure, well, we'll call MIT. It must be someone at MIT knows how to do whatever it is. So this guy calls up from Alabama, and he says, and it gets referred to me as a young assistant professor, and he says, I need to cut aluminum. I said, well, yeah, cut aluminum. You can hacksaw it or you can bandsaw it. And he says, no, I don't think that's going to work. I said, well, what's the problem? He says, well, this is pretty thick. I said, well, how thick is it? He says, oh, it's about 1.5 feet thick. I said, that bandsaws will cut something 1.5 feet thick. No, I don't think it's going to work. And I said, well, what happened? What is it that you got? He says, well, he works in a foundry, and they had a big melting pot of aluminum. They just would melt aluminum, and when they were ready to cast, they would tilt the furnace, and they'd pour the aluminum out. Well, they lost power, and the pot froze up. And so they had this 1.5 feet of aluminum inside this pot, melting pot of aluminum. And I said, you got a problem. And I didn't know the answer. Now, I know if it had been steel, and those types of things happen in steel mills. In fact, there's a story, one of my classmates went off to a steel company when we were undergraduates one summer, and at the plant they were at, they were melting this 200-ton, batch of steel, and in the control room you have this hourly worker, union guy, who looks up at the, he watches the gauges and stuff, and then you have engineers supervising these people. And the engineer comes in, he looks up at the gauges, and he can see from the gauges the weight of steel in the vessel, the steel still in the vessel. He says, well, I want you to tap the heat, which means pour the steel. And the engineer walks out of the room. He comes back about 10-15 minutes later, and he looks up, and the steel's still in the vessel. And he looks up at the gauges and see the weight of the steel in there. And he says, well, I told you to tap the heat. And the guy says, but. He said, don't give me any buts. I told you to do it. And so the guy does. He taps it. The reason he hadn't tapped it before is because the railroad car to accept the steel had not come up. Okay? And so he just tapped it on top of the railroad tracks. And so you had 200 tons of steel casting all on the floor of the shop. Now, the floor of the shop happens to be dirt with railroad tracks, okay, and steel mill plant. It's just a dirt floor because you sometimes have breakouts on it you know, unintentionally. This was intentionally poured on the floor. Anyway, they both lost their job. However, how do you clean that up? Well, then now you got about 1.5 feet of steel on the floor, and the guy just goes in there with an oxygen lance, and they cut it out. It takes them about a week to clean up 200 tons of steel. With an oxygen lance, you basically cut it into smaller chunks, and you move it out, and you remelt the steel, and you clean up the area. Now, the reason you don't like to dump it on the floor is there can be people on the floor, and people die from things like that. So that's why they both lost their job, even the union guy. So there's a little moral to the story. I mean, you ought to at least listen to the person's explanation, you know. That's supposedly a true story. Getting back to the aluminum, though, you can't flame cut aluminum, so you can't just go inside a pot and just take a torch. And plasma torches won't cut more than an inch or two deep, and so something that's 1.5 feet deep, yeah, you can try to carve the thing out, but that's kind of trying to like whittle away the Statue of Liberty with a penknife or something, right? It's not going to work very fast. So I really didn't know, and I told him I didn't have a solution for him. I don't know what happened to his problem. But about 10, 15 years later, I was sitting having dinner up in Harvard Square at some restaurant when there was a vice president of Alcoa there, and I said, I'd always remember this situation, and I said, you know, you guys must have, when you make aluminum, you have these great big aluminum pots, and they have about 1.5 feet of aluminum in them. I said, you guys must have freeze-ups in those things sometimes. And he says, yeah. I said, well, how do you fix them? He says, well, there's this guy in Pittsburgh, and it turns out, when you have a freeze-up in an aluminum pot anywhere in the world, this guy's kind of like the Adair of aluminum pot lines. You know what Adair is? Adair is the guy who blows out oil well fires. You know, he goes up with his crane and he sets off an explosive charge to blow out the candle. You know, Adair was the world's expert in oil well fires, and before Kuwait, it took him sometimes a couple of weeks, sometimes it takes 2 months to put out an oil well fire, because they're pretty hot and you can't get close to them. But basically, just go up with a great big crane and some explosives, you lay it down there next to the fire, and you set off the explosion, and you're just blowing away. It's just like blowing out a candle, a big candle, okay? Now, the problem is you also have to have water going on it so that it doesn't reignite, right? Because there's some hot pieces of metal around that could reignite the steel. But anyway, so Adair he was the world's expert on blowing out oil well fires, 50s, 60s, 70s, 80s, and then into the 90s, his company, and they made a fortune because, you know, no one else in the world could do it. And then after Kuwait, when you had all these oil well fires that were set, they thought it was going to take them 1.5 years to put out all the oil well fires. But there's something called a learning curve, and they came down the learning curve, and they basically, I think they had it all out in like 6 weeks or 2 months, because they got so good, so much practice, that now you can put out oil well fires much faster. Well, anyway, this guy in Pittsburgh essentially does the same thing. He blows pot lines. And the only way to, if you have a big casting of aluminum that froze up, you basically drill some holes, you put some charges in, and you blow it. And I said, well, does it always work? And the guy says, well, not always. Sometimes you lose your whole pot line, but you know, you've lost it anyway, it's full of aluminum. But sometimes it works, and if you get it right and stuff fractures the right way, then you blow the aluminum into little chunks. So that's how you got aluminum, is the right thing.
Why can't you just reheat it?
Because it has to do with how the furnaces run. A lot of these furnaces are run electric, well, they're electric furnaces in many cases, and and I don't know the details of the design of the furnace, but basically you either plug up some of the gas holes, or if it's gas fired, or electrically you have too much. You don't have enough resistance in your system to keep it hot, to get it up to temperature. Your incoming bus bars can't carry enough current to reheat it, okay? And most of these things, you can't just put another furnace around it to heat the whole thing up. Frankly, I don't know all the details, but I do know that if it freezes up in there, you've got a big problem. Okay, so that's how you cut aluminum. You call the guy in Pittsburgh. I don't have his phone.
I was using aluminum ladle or an aluminum pot for aluminum.
Oh, you don't use aluminum pots. You use typically use a refractory magnesium or aluminum oxide, or you can use actually aluminum. You can use clay graphite. The big aluminum pot lines where they refine the aluminum, that's basically graphite or some kind of carbon.
I was going to say something like melt steel or something, and put the molten steel on top of the aluminum to kind of
Well, you could, except iron and aluminum form in a high melting intermetallic that melts about 2,000 degrees centigrade. So what you'll do is you'll form a diffusion layer that stops everything else. Okay. So now, if you had a jet of liquid iron, you could kind of cut through the aluminum because now you're going to be blowing away that stuff, right? So if you had a liquid metal jet, you could cut through the aluminum. And I won't say any more. That's confidentiality.
I have a question.
Yes.
Before you said you can add iron powder to the fuel and oxygen mixture to cut stainless steel.
Right.
And well, what about the magnesium that's in the stainless steel? Isn't the melting point of the magnesium a lot lower? Isn't that the problem with getting cut in stainless steel?
You're thinking of manganese. Magnesium.
Okay.
Manganese is roughly the same melting point, Mn rather than Mg. Okay. Magnesium actually is used in steel, or not steel, but in cast iron. Anybody know what ductile iron is? There's different types of cast iron. And what's ductile iron?
Well, there's white iron and there's white cast iron. I can't remember all of them.
Okay. Yeah. There's different grades of cast iron. White iron is a cast iron that cooled rapidly enough that you get a martensitic structure, and it's very hard, very abrasion resistant. Gray cast iron, and the reason it's called white cast iron is if you polish it and look at it, it basically looks white in a microscope. It reflects as silvery. Gray cast iron is a dull gray, and that's what most cast iron, if you have a Christmas tree stand, or you have andirons that go in the fireplace or something, those are just cheap, ordinary gray cast iron. Gray cast iron has got very poor fracture resistance because it has these little flakes of graphite, which are perfect little crack starters. If you look at the fracture toughness and you look at these flakes of graphite, they're on the order of the critical flaw size. You know, they're getting up towards the critical flaw size. So gray cast iron is fairly brittle. Then they have what is called malleable iron. In the old days, in order to take the gray cast iron, which has you cast gray cast iron, and it has these flakes of graphite in here. You can heat that in the furnace for a long period of time, and you can make malleable iron, and then you kind of get the graphite flakes will kind of, what we call coarsen to little kind of cauliflower graphite pieces. In malleable iron, now you got iron without these long flaky things, and you basically get good ductility. Problem is, a malleabilizing furnace, if you're talking $1,000 an hour for the furnace, you're talking about 24 hours or 48 hours heat treatment to do that, and you're taking a very inexpensive gray cast iron and turning it into expensive iron. Back around just mid-century last century, they learned that if you put magnesium into liquid iron, that you can actually get it to nucleate spherical instead of flakes. You can get little round actually called spherulites. You can look at them, the carbon kind of grows in all kinds of little different directions like that. But you now have, so sometimes it's called nodular iron. You have little spheres of graphite, and that forms on solidification, and that's called ductile iron. And all the cast iron sewer pipe and everything that's made nowadays is nodular iron, or ductile iron. The problem is, manganese boils at 650, or melts at 650. It boils at around 900 C. Cast iron melts at 1200 C. So I'm putting something that, and it turns out the magnesium doesn't alloy very highly with the iron. So you have a big pot of gray cast iron. It's not gray cast iron, it's just liquid cast iron because it hasn't solidified yet. And you take a sphere, or you take some canister that has the magnesium in it on a rod, and you plunge it to the bottom of this thing quickly and hope that it reacts before it vaporizes and explodes. Okay. Now people have gotten better at it. There's a learning curve there too, and so they very rarely flow liquid cast iron all over the room. But if the magnesium doesn't, if you don't add the magnesium the right way, you'll basically get magnesium vapor, and it'll blow all over the cast iron all over the foundry. And so it's not that neat to have molten iron raining down on you. Anyway, so that's how you make gray cast iron, or gray cast iron is nodular iron. That's magnesium. Manganese is an iron mixed together without any problems. Okay. See, I can tell you stories from last time. Anything else?
I heard that Bethlehem Steel is filing for bankruptcy this morning.
It's about time. I used to work for them, and let me just say that the seeds of this were sown in the 1970s with a management that thought they still ruled the world. I remember that the week I left Bethlehem Steel, and it wasn't just U.S. Steel, it wasn't just Bethlehem, it was U.S. Steel. The Edgar Spear was his name, was the chairman of U.S. Steel, and there on the cover of Iron Age magazine, this is 1976, right? I'm sure you all read Iron Age, right? We weren't even born, some of these. In any case, there on the cover was Edgar Spear, who was not only chairman of U.S. Steel, he was the president of the American Iron and Steel Institute. And you read the article inside, he says, well, the Japanese aren't using anything we don't know about. Now think about that quote. The Japanese were using the new technology, and we knew about it. We weren't using it, okay? So, I mean, you know, that was the mentality of the American steel industry in 1975. These guys that were managing Bethlehem and U.S. Steel in 1975 had been hired in after World War II when the United States controlled 75% of the world steel business. Those two companies alone controlled 40% of the world steel business. It was basically a cartel. And they blew money. I mean, I live near the Allentown Airport, and they had these corporate jets. And the vice presidents of Bethlehem Steel would take the corporate jet down to Florida on the weekends to play golf. You go to the wood shop at the research labs, and they're building this beautiful dining room set. Okay, you know, they had a country club that was just, you know, like nothing you see anywhere else except maybe in the automotive industry or at Microsoft or something like that today. Okay. Companies that get a semi-monopoly and are making a fortune actually have to hide money. I mean, I learned that in the mid-'80s or late 80s, early 90s, when I first went to visit Kodak. Kodak had this thing, it was printing money. Basically, it was silver film, okay, but they had practically a worldwide monopoly until Fuji started competing with them. And that's an interesting story, too, because in the that wasn't necessarily bad management at Kodak. In the 60s, Kodak asked the Japanese government if they could build a film plant in Japan. Because you still, I think the rules in Japan are, if you want to build, if an outside company wants to build a plant in Japan, you have to ask the Japanese government's permission. Well, in typical Japanese fashion, they didn't tell Kodak no, they also didn't tell them yes. Kodak's still waiting for an answer, whether they can build a plant in Japan. And basically the Japanese government stonewalled. Fuji was able to build a plant, take over the Japanese market, and then eventually grow into the rest of the world. Even though Fuji's quality was so far inferior to Kodak, if they didn't have that protected market in Japan, and the Japanese mentality of purchase Japanese as opposed to anything else, Fuji never would have been able to get down the learning curve and make a decent quality film. And Kodak would have continued with their monopoly, or semi-monopoly. I remember visiting Kodak early 90s for the first time, and you know, there was this one place where they had boxes that had to go from here to over there to up to the next floor. Now, most companies would go, you know, look in a catalog and find a conveyor system, you know, that would, you know, do that. Not at Kodak. Kodak had been making so much money in the early 80s. They basically, I think, these companies get to the point they have to hide their profits. Microsoft is kind of the same way today. Okay, if the government saw how profitable they really were. I mean, I remember when Lotus 123 started up, and most of you were still in diapers, but it was right over here, and Lotus was just minting money when they were the only spreadsheet program around, you know, in the early 80s. And they had buses that took people shopping at lunch. okay? I mean, they were just throwing money around like it was going out of style, because they had to hide it, because if the government saw how profitable they would come in and do something about it, okay? And so at Kodak, to move these boxes, they didn't go out and get some garden variety conveyor system. They had their own engineers design a stainless steel conveyor system. This was just moving boxes, okay? Custom built out of stainless steel. Now, who in their right mind would ever do this, okay? But it's not a question of right mind. They had to hide their profits. They no longer have this problem, okay? They actually have competition. But it still amazes me to see industries where a company gets a monopoly and just is making, you know, Intel was like that a few years ago. Microsoft is that way today. U.S. Steel and Bethlehem Steel were like that after World War II. And what happened is those engineers or managers, they got hired into the steel companies that were after World War II. They controlled the world market. When in the early 60s, when U.S. Steel wanted to raise the prices, President Kennedy stonewalled them or didn't stonewall. He basically stared them down and said, you can't raise prices, because if the steel company got a 5% price hike or whatever in the United States in the early 60s, it was going to cause worldwide inflation. And so President Kennedy basically, you know, there was this big standoff and he forced them to roll back the prices. The American steel companies will blame that as that was the beginning of the end for them, because they weren't able to keep their profitability up. They could have kept their profitability up if they didn't just burn the money, okay? I mean, I was there when they were still in the burning mode. They weren't doing it by paying me a big fat paycheck necessarily. You know, it was a fair pay, but it wasn't, you know, but it was, they were taking care of their bosses. And one of the first things you need to learn when you go out and look for a job is look and see if they have assigned parking spaces. Okay? And what does that tell you? Okay? First, it tells you it's a two-class society, right? I prefer the companies where there are no assigned parking spaces. Whoever gets there first, whoever's working the hardest, gets the best parking space, okay? As opposed to the boss. MIT has 4 assigned parking spaces, or 5 or 6 over here, for the provost, the chancellor, the president, and the chairman, okay? They're reserved and they're usually empty because the president's house, he walks to work, okay? But he's got the only, aside from the physical plant maintenance vehicles, the only assigned parking spaces I know of at MIT are those 4 over there, okay? But yes, they do. And the MIT administration has its problems too. But that will take more than this discussion.
We got 10 days.
The problem, in a nutshell, the problems of the MIT administration are just like any other big organization. The managers get to think that they are what runs the business. It's the people, you know, at the lower levels who actually do the work. The managers are supposed to be helping those people, and it's a question of managers should be serving the people that work for them rather than thinking it's the other way around. And at Bethlehem Steel, it was big time. We were the servants of the managers. I mean, when I was there, the chairman of the corporation's daughter was getting married, and his wife, they just moved into a new home, and his wife didn't like the color of the bathroom. So the Bethlehem Steel maintenance department from the plant had to install a new bathroom in less than a week's time. At company expense, of course, right? I mean, it didn't get billed through to him, right? It's, you know, nowadays you'd often call something like that corruption, but, you know,
It still happens.
still happens. If the IRS knew about some of these things, I'm sure that they would probably, what they could do is say it's earned income and you got to pay taxes on it. But you know, no one was going to do that. You should treat people as equals and respect the work of the people, the laborers who are actually doing the work. And unfortunately, MIT is turning down that and getting into that road of the managers think that they are the ones who are doing the research and doing the teaching and things like that. Okay, but that's a common problem. But that's one of the first things you look for is, you know, how many assigned parking spaces do they have? Okay, I'll tell you some other secrets. Okay, art. We ought to get to art. Although There was one other thing I was going to talk. One other thing, someone suggested that I tell you a little bit about how to get through MIT. When I put up these little bullets, there's 2 or 3 or sometimes 4 of them a day, and that's the review of what we did the last time. All you need to remember about the previous lecture is something as simple as that, and that's all you will remember. Robert Hutchins, who's now editor of great books of the rest of the Western world, but was the great president of the University of Chicago and made it a great university system, said, "The mind is not a receptacle, information is not education. Education is what remains after everything you've learned has been forgotten." Okay? So, in most classes, not in this class because you don't have a quiz coming up, in most classes you have to learn some details so that you can pass the quiz. But you'll never need those details ever again in your life. What you will remember is a few simple little principles. And right now, you need to kind of think in terms of boundary layers. Earlier in this semester, you need to think in terms of surface roughness and surface contamination. But boundary layers are somehow limiting the heat transfer of whether it's arcs or electron beams or whatever. And I learned all that stuff basically it wasn't this classroom, but it was this spot right here. I took as a sophomore, no, as a junior, first term junior, Introduction to Quantum Mechanics in this room. Okay, well, it was raised up that way rather than sloped that way, and I was sitting right about over there. Okay, and Vera Kistiakowski was the professor of physics. Her father had won the Nobel Prize up at Harvard. And Vera is retired now, but she used to always bring her dog, her German Shepherd, to class. And I didn't have the foggiest idea what was going on in this class. I mean, we had a book called Iceberg Fundamentals of Modern Physics, and I didn't understand what was going on in the book. And she'd get up and she started lecturing about something, and I didn't have the foggiest idea what was going on. I was averaging about 15 out of 100 on the homeworks when the rest of the class was averaging about 85. Okay? So the night before the final, I just thought, there's no way I'm going to figure all this out. I'll just go through the book and try to figure out the highlights. When I walked into the exam the next day, 3-hour exam, sat right about over there, and I finished the exam in an hour, checked it over in another 15 minutes, had to wait another 15 minutes because she wouldn't let anyone leave before the first hour and a half. Okay? So I sat there and twiddled my thumbs for 15 minutes, turned it in, got an A in the course. I probably got close to 100 on that exam, even though I didn't know beans about the whole subject. Because I just decided I was just going to try to pick up the high points. And that was the great revelation to me, that all it is a series of high points. And the professor is trying to hide his outline of what the topics are. He just comes in, the professors will come in and they just shoot a bunch of information at you, okay? And you sit there furiously taking notes, right? And you never have time to step back and say, what are the 2 or 3 key points? Because in an hour's lecture, you can only make 2 or 3 key points. That's it. Last lecture, there were 3 points, okay? I'm giving you the 3 points. Well, for the rest of my MIT career, I basically quit taking notes in class. I just sat back and tried to figure out what's the professor's outline, because he was hiding it from me. And if I could figure out his outline and figure out the 2 or 3 points, I got the fundamentals, and all the other details just kind of flowed from it. You're all smart enough to fill in the details, okay? So that's one of the reasons I do this, is because I'm trying to help you learn as opposed to hide the information from you, which is the typical teaching technique at a university. It's not unique to MIT. It's virtually anywhere. The professor wants to fill your mind with all this information, but as Hutchins says, the mind's not a receptacle. We don't just fill it up. Information is not education. Just passing on data or deriving a differential equation on the board or something, or doing a proof. Well, you've heard my statement about proofs in class, right? The professor did the proof or derived the equation in class because they didn't have time to prepare a lecture. I mean, I've done it. If you have to teach, you realize, oh, I didn't have a lecture today, I'll just derive this equation for him and fill the hour. Okay? That is the mentality. I've only had to do it 2 or 3 times in my life. But the reasons I did it was because I didn't have time to prepare the lecture, but I can easily pull out a proof and throw it on the board and fill the hour. I'm killing time. Same type of thing right now. I actually did prepare a lecture today, but I'm telling you stories because some of these stories are more useful. Okay, arcs are electrically augmented flames. This is a Tom Eager definition. You won't find this anywhere else. We said we have a boundary layer, and that limits the heat transfer to the surface of something. The maximum heat intensity I can get, typically with a flame, a pre-mixed flame, is about 1,000 watts per square centimeter. With a jet burner, where I get very high velocities, but not higher temperatures, right? Because it's still maximum near the 80 bag flame temperature. But a jet burner, I'm igniting inside a constant volume, and so it shoots out at very high velocity. I might get 2,000 watts per square centimeter as a heat intensity on the surface with a jet burner. With an arc, I can get 10,000 watts per square centimeter. And the reason is, with an electric arc, I've got an electrode up here, I've got a surface here, and I have these electrons flowing. I actually have a boundary layer. I have the gas coming in, and I have the gas going across. But the thing that's neat about an arc is the electrons punch right through it. And it turns out that, I'm going to show you later, 90% of the heat is carried by the electrons in an arc. So if the boundary layer is limited to 1,000 watts per square centimeter, but I can get 90% of my heat by this, I can get 10,000 watts per square centimeter, because 9,000 comes from the electrons and 1,000 across the gas boundary layer. And so what I've done with an arc, by applying electric current, I'm using electrons, because they're smaller than ions, to punch through the boundary layers. It turns out that in an arc, 99% of the current is carried by the electrons. The other 1% is carried by the ions. An arc is electrical plasma, electrically generated plasma. Plasma is just, some people say plasmas are the fourth state of matter. I don't like that definition because thermodynamically, if you talk states of matter, you're really talking phases. And the way Gibbs defined a phase, I think that's, there's not a sharp phase transition between a plasma and an arc, a neutral gas and a charged gas. So, in any case, whether you consider a plasma a fourth state of matter or not, basically you take a neutral gas and you separate it into positive and negative charges. And so I have positive ions. If this is the negative electrode and this is the positive electrode down here, the positive ions are going to go that way, the electrons are going to go this way. However, the electrons have about 100 times the mobility of the ions because they're nice and light. So they move much faster, about 100 times as fast, which means that 99% of the current is carried by the faster moving electrons and only 1% by the ions. Now, see, I did prepare a lecture. I couldn't have done that if I hadn't prepared it. Anyway, but actually it was a student requested that I tell you how to get through MIT. And the way to get through is just figure out what the high points are and go to the lecture recognizing that the professors are only going to test you on the high points. And you can usually psych out the quizzes. And I remember going in for a quiz once, or the day before a quiz, and Professor Pepper, who was a wonderful man, but he was German, and he had gotten his law degree or business degree, or maybe both, from Harvard, and then he came over here and got a PhD or a Doctor of Science in metallurgy and became a professor here. So he was a real stickler for the English language, grammar and things like that. He was also a real stickler for a lot of things, but he was very formal. We had to bring our textbooks to class, and he would make us open them up and stuff. Anyway, he says, some student asked, well, how many questions are going to be on the exam tomorrow, Professor? He says, 6 questions, but I can't tell you what's on them. I said, yeah, but we already know what's on them. He looks at me, because I'm just a student in class, right? He says, what do you mean, Mr. Eager? I said, well, we've covered this topic, this topic, this topic, and this topic, and so you're going to have a question on those 4. And then you're going to have to ask us this, because we didn't do well last quiz on that. And then the last question is going to be on this topic or that topic. And he looks at me and says, well, we'll see. I was right. I mean, if you start realizing what the basic outline is, you can figure these things out. Now, where was I? I was going to draw you. If I have this arc and I plot the voltage, I'm going to plot it sideways here. The voltage, I will have, from a negative voltage to a positive voltage, a voltage profile that looks like this as I go across the arc. Okay, so this is just a graph of the voltage. In this region right in here, it's called the cathode, because the negative electrode is the cathode. The cathode fall region, and down here they have this clever name, they call this the anode fall. And this is called the plasma column in the middle. In the plasma column, you have an electric field strength of about 8 to 10 volts per centimeter. But in the cathode fall and the anode fall regions, you have much higher voltages. If this is an atmospheric pressure arc, 1 atmosphere overall pressure, this total, if this is a tungsten electrode up here, the total voltage here might be 10 to 15 volts for a tungsten electrode. This distance might be half a centimeter or a centimeter. If you put all this together, it turns out that if this is, let's say this is a centimeter, that's a pretty long welding arc for gas tungsten arc, but this would be a gas tungsten arc with a tungsten electrode. And you would have argon as a shielding gas. But the plasma fall region, if this is, these little regions are only about 1/10 of a millimeter in length. So I could have 8 volts drop across here, and that means these other regions I would have, in these other anode fall and cathode fall regions, I would maybe have another 8 volts or 7 volts or so falling across there. Now there's some other, if this was a steel electrode, this might be a 25 amp or 25 volt or 30 volt arc. But order of magnitude is a few tens of volts. And it turns out these fall regions are typically cathode fall, and the anode fall might be 4 to 5 or 2 to 4 volts. Yeah, we'll get into some more of that later. It depends on the material. And what's happening here is, in these regions, I'm next to something that's relatively cold. Like this tungsten may only be at 2500 centigrade. That's relatively cold. You may not want to hold it in your hand. And this might be molten steel down here. You may not want to hold that in your hand at 1600 centigrade. But compared to the plasma at 10 to 15,000 Kelvin, they're cold. And the cold gas next to this forms essentially a cold sheath region, sometimes called a sheath. The cold sheath doesn't have a lot of free electrons. I have to be at very, very high temperatures for my electrons to be stripped off by thermal energy from the ions. If I look at, this is the phase diagram for argon, and we plot it as particle density versus temperature. This is in 10 to the 19th particles per cubic centimeter, which is about 1 atmosphere pressure, okay? But anyway, well actually this is thermoplasma atmospheric pressure. So this is 1 atmosphere pressure, but if I'm at, well, this is in thousands of degrees Kelvin. So room temperature is right in here somewhere, and 10 to the 19th is something around atmospheric pressure density. 10 to the 19th particles per cubic centimeter. Somewhere around in there is atmospheric pressure. This line right here is just PV is equal to nRT. That's just a hyperbola. That's the total number of particles. PV is equal to nRT. That's the N of nRT. That's the particle density in particles per cubic centimeter. If I go up in temperature, at some point, this is in a gas, not a plasma, argon gas, the number of particles equals the number of argon atoms. Well, this line right here with the A is the the argon atoms. Okay? If that line continues in here, this is the neutral gas. When the argon atoms start deviating from the total number of particles, it's because the number of argon ions are coming up like this. From orders of magnitude down, almost no ions in the gas, to up here, right at this temperature, which happens to be at about 14,000 Kelvin, the number of argon atoms equals the number of argon ions. I'm 50% ionized in the plasma. If I keep on going across here, the argon ion line separates and goes down, and the number of electrons, this Ne is the number of electrons in the plasma. Initially, the number of electrons and the number of argon ions were the same line. Okay, charge conservation. However, once this one starts deviating, it's because the argon plus is coming up. And eventually that one goes down, and the argon 3 plus comes up. Well, you'll never see argon 2 plus and 3 plus in a welding plasma. In fact, a welding plasma is typically about 5% ionized. You can go through the mobility of these electrons, and you can say, I've got a plasma of this diameter in argon, and plug in the mobility, and say I'm going to have 100 amps or 200 amps. And say, how many electrons do I need with that mobility to carry the current? And to carry 100 or 200 or even 1,000 amps, you only need 5 to 20% ionized in that plasma. And so it turns out the plasma temperature is naturally controlled by the fact the system wants to generate enough electrons to carry the current. If I change from argon to something that's more easily ionized, like krypton, bigger inert gas, but the outer shell electrons are not as tightly bound because it's a bigger atom and there's more shells of electrons screening the nucleus, right? I'm going to have a lower temperature. The krypton phase diagram is going to look just like this, except shifted over this way a little bit, squeezed over this way to lower temperatures. And metal vapors, like iron or aluminum, are squeezed way over even further. In fact, if this was an iron vapor phase diagram, it would be squeezed over, and you would find that at 5 to 30% ionized, you would only have a temperature of maybe 6 Kelvin. 6,000 Kelvin, not 6 Kelvin. It's pretty cold. 6,000 Kelvin. So it turns out the welding arc, typically, you can think of it as around a 10,000 Kelvin arc, because I'm driving it with an electrical power source, which is forcing a current through it. I'm fixing the current going across this thing. Nature will pick the lowest possible temperature to give me enough electrons to produce that current. If I up the current, if I turn up my power supply, I'll get a slight increase in temperature. What's the increase in temperature? 50 degrees Kelvin is enough to double the current when I'm at 10,000 Kelvin. So you can't even measure the difference in temperature when you increase the current. Now you start getting to 100,000 amps, which we don't weld with, but we melt steel with in an arc furnace. You will start getting to a higher temperature, and you could actually measure it. It might be, instead of 10,000 Kelvin, it might be a 15,000 Kelvin arc. I mean, you do have to push up eventually when you put enough current through there. But for any welding currents, the temperature of the plasma is controlled more by the amount of iron or aluminum or whatever metal vapor impurity, because those things give off electrons even easier than the argon does. Okay? So that's enough for today. We will meet tomorrow, and I've got to go to Washington. I found out this weekend on Wednesday and probably Thursday. I'll let you know more today when I straighten out my schedule this week. Hopefully we will be able to meet, well, we will meet tomorrow, and hopefully we will also be meeting on Friday, but I will confirm tomorrow. But I know we're off on Wednesday, and I think we're probably off on Thursday because of this meeting in Washington. Which means that we still should finish up by the end of next week. Okay? I don't want to drag on to the next week.